Okay, so thank you, and thank you for the invitation. You heard a talk about the electromagnetic calorimeters proposed by the CALICE collaboration. Now I will speak about the hadronic calorimeters. I start with a reminder. These calorimeters proposed by CALICE are optimized for particle flow. Particle flow is the optimal approach to reconstruct final states in E plus E minus collisions. You have an illustration of this here with an event with WW decaying into 4 quarks. So this is optimal, especially when you have jets, taus, in your final states. And you need to have optimized detectors to be able to use particle flow algorithm. And this optimization is done by having compact detectors, especially calorimeters that fits inside the magnets, with negligible dead zones to have fine segmentation without sacrificing the intrinsic energy resolution. So you need to carefully select the technology that is used for your subdetectors. In CALICE, there are many solutions that are proposed. Okay, you see them here. Here I will talk about the one in the blue circles. So HCAL, analog and digital, using scintillators or RPCs. So here we are talking about sampling calorimeters. So we have absorbers and detector planes. For the detector planes, one of the solutions is to use RPCs. So the idea is that every time you have a charged particle that crosses the RPC, you have an avalanche and you obtain a macroscopic signal. You have an illustration here of the amplification, number of electrons. Okay. So you have here an illustration of the amplification of an RPC, number of electrons versus distance. So this illustrates that this is an efficient detector. So you end up with a macroscopic signal starting from a few electrons with a reasonable background. It is linear. So when you have several particles crossing the RPC, you have a signal that is proportional. The avalanches are also well contained. So if you are capable to segment the way you collect the charges, you can have segmented calorimeter. And it is not expensive detector and robust. However, it requires a careful choice of the resistive material that you use and its operation, like the choice of the gas, the high voltage, in order to avoid saturations. So the HCAL solution is based on RPCs, glass RPCs that are 1 millimeter, using 1 millimeter gaps. And the charges are collected with pads that are 1 centimeter square segmented. Now, another possibility is to use for the detector planes scintillators. Scintillators are used since a long time for calorimeters. They are fast, well linear, and the light produced by the scintillators when charged particles cross them can be routed to photomultipliers. Here the proposal in the HCAL is to use silicon photomultipliers. They have a high gain. This is an illustration, not necessarily the one used for HCAL, where you see the peaks corresponding to the various photoelectrons. So you have a nice linearity. However, they require some calibration. They are very sensitive to the temperature, for example, and you need also to study the scalability, how to build a large detector assembling all these pieces. So in order to validate these technologies, prototypes were built and tested. So the first one I described here is the analog HCAL physics prototype. So the aim is to validate the technology, but also to study the simulations and hadronic showers, because with this fine granularity, there are things to learn from test beam data, and also to show that it is possible to have a robust calibration chain with scintillators and silicon PMTs in a calorimeter. And this is, in fact, the first large-scale application of silicon photomultipliers combined with scintillators in a calorimeter. In this prototype, there are 38 layers, so this is the longitudinal segmentation, while the scintillator tiles are segmented as 3 times 3 or 12 times 12 centimeters square, and the thickness is half centimeter. There's no cooling inside the active layers. However, the readout is outside the prototype, so this is a bit different from the final detector expect at ILC. And in the prototype, there are about 8,000 channels with a dedicated readout. It was tested in test beam campaigns since 2006 at DAISY, CERN, CNAL, using hadrons, muons, electrons, including a calibration system based on LED sources. So this calibration is quite important. So the approach of the calibration with such a detector is done in 3 steps. The response of the cells is equalized using MIP particles, muons typically. Then the SEPM gain is monitored, and also corrections for nonlinearities are included. And finally, the calibration from MIP to GV is performed using electrons, so at the electromagnetic scale. Using LED light, the calibration of the silicon photomultipliers is performed. You see here the response corresponding to the various number of photoelectrons. And concerning the linearity, so this device is intrinsically nonlinear due to the limited number of pixels and also to the relaxation time between 20 nanosecond to 1 microsecond. But this nonlinearity is understood and can be well modeled and measured, which means that it can be corrected. And you see here how this correction looks like, but maybe more clear on this plot. You see here the response of the HCAL in MIPS to different positron energies. If you fit each Gaussian and you report the mean value as a function of the beam energy, you obtain these blue triangles. So you see this nonlinearity due to the saturations. And if you introduce the nonlinearity correction of the silicon photomultipliers, you obtain these black dots. So you restore most of the linearity. And the slope of this curve gives you the calibration constants from MIP to GV at the electromagnetic scale. So now we have the detector that is calibrated at the electromagnetic scale, but you want to use it with hadrons. The hadron showers are different from the electromagnetic showers. So you could just use this calibration plus a scale factor, which is typically 20%, and use it like it is with pions. But you want to really use all the potential of a segmented detector. The segmentation of the detector gives an information on the electromagnetic component just by using the topology of the shower. So even if this is a non-compensated calorimeter, we can use a software compensation. So the idea is to reweight the energy cells with a weight that depends on the energy density. And the energy density is the experimental way to know if the energy deposits is more electromagnetic or hadronic. And you see here the distribution of the energy density in the HCAL. And these weights have some free parameters that you measure by minimizing a chi-square that basically compare the reconstructed energy to the beam energy. And you see here how these weights look like. Here is the impact of this software compensation. In black, you see the reconstructed energy in GV at the electromagnetic scale using 10 GV pions. And in blue, including this software compensation, and the gain in terms of resolution is quite obvious. So this is true at 10 GeV, but also with 80 GeV pions. This gain is quantified on this plot, where you see the energy resolution versus beam energy, in black without any correction, and here in red and blue using these software compensation. The linearity is good in any case, between 1 and 2%. So this is for the energy reconstruction using this prototype with the HCAL. The same, let's say, validation was done with the HCAL proposal. So a technological prototype was built. So the HCAL, we have 48 layers. So this is the longitudinal segmentation. Each layer is 1 meter square, and the readout is embedded in the detector. This is a semi-digital calorimeter, which means that for each pad we have 4 states, 2 signal and 3 levels. The granularity is 1 centimeter square, so this corresponds to something like 10,000 pads per layer and a total of 500,000 channels. And the power pulsing is included. So it was tested in test beam from 2012 to 2017. One of the important points is that this is the first test of the power pulsing with such a detector. And as for the HCAL, the performances were measured. You see here the efficiency per layer using muons. So it's better than 90%, except for one pathological layer here. And then for the energy reconstruction, you want also to use this granularity and the fact that you can go in the structure of the shower. So you see here a pion interacting in the HCAL with the hits. You see the 3 colors corresponding to the 3 thresholds, the first, the second, and the third, in green, blue, and red. And this is correlated to the electromagnetic part of the hadronic shower. Now, if this can be used for simple identification. For example, here you see what we obtain with a muon, here with a pion, and here with an electron. But you can use it also for the energy reconstruction. The energy can be reconstructed in a naive way just by using the number of hits. So there is a proportionality between number of hits and energy. You can determine this relation by, again, minimizing chi-square, and you see the linearity of the energy reconstructed in this way. But you can also use the 3 thresholds, so number of hits passing the first, second, and third thresholds, so in a more complex relation. Again, you tune some free parameters using test beam data. You get a well-linear response, but the gain is visible on the energy resolution. So here you see the energy resolution versus beam energy in red using a simple binary mode. So this is a pure digital calorimeter where you have only hits. And in blue, if you use these 3 thresholds. And the gain is significant for energies larger than 30 GeV. So this is for the energy reconstruction, but for a particle flow approach, the important thing is to be capable to reconstruct the clusters and to make association or separation between them. So you need to do some imaging. One thing that was done is to identify the tracks inside the hadronic showers. You see here with an HCAL event and here HCAL event. You want to do this for several reasons. This is very useful for the particle flow. For example, here, the fact that you have some hits but that you identify tracks help you to connect these 2 clusters that belong to the same pion. You can also use these tracks for the energy reconstruction by assigning a different weight to these hits. And you can also use these tracks to make some in situ calibration. The method that is commonly used, both in the analog hadronic calorimeter and HCAL, is the House transform method. As an illustration, we can see here the number of reconstructed tracks in the SD HCAL using electrons in red, and here using pions. And you see that this can help to separate showers that are electromagnetic from hadronic showers. You can also use this to tune some your simulation and some models that are very sensitive to the topology of the shower. You see here with the AHCAL the track multiplicity measured in the data for 25 GeV pions and compared to different models, and same thing here in the SD HCAL. One word on the particle flow, because this is something that needs to be studied in the framework of a large detector like ILD, but some tests can be done still with the prototype using test beam data, for example, by merging pions coming from two different events, and by quantifying the probability to separate these two pions as a function of the distance between the showers. So this is with the AHCAL and the SD HCAL. Okay, it's not exactly the same estimator that is used, but the message is that in the case of the HCAL, you have a trend. It's more and more difficult to separate showers when you have a small distance between them. In the case of the SD HCAL, you have a quite excellent separation and a sort of threshold below 10 centimeters, under which it's difficult to make the separation. So this is for the prototype. Now, the next step is to demonstrate that it is possible to move from these small-scale prototypes to realistic detector modules. The final detector won't be a cube. It will have some structure like this for the AHCAL or like this for the SD HCAL. So you see here the barrels proposed for ILD using AHCAL and SD HCAL. They have to fit inside the magnets. It means for the AHCAL to have the electronics embedded inside the models with the services here. For the SD HCAL to have models with this geometry. And you have also to demonstrate that you can make a large-scale production. For the AHCAL, so the physics prototype I have shown has excellent performances, but is not scalable to a collider detector because the electronics is external, because the calibration system based on the LED is also external, and the assembly is difficult. So the next step, which is ongoing, is to build a technological prototype, and the optimization, especially for the assembly, concern the interfaces. How to connect the scintillators to the sensors to the PCB, the scintillators to the PCB, scintillators to the LEDs used for the calibration. For example, should we keep fibers and so on. So a choice was made, so here I give directly the conclusion, to mount directly the scintillators on the SEPM in this way, while the SEPM that you see here are directly mounted on the PCB. Many tests were performed in test beam with small prototypes, and also using radioactive sources to show that there is no homogeneity problem. And so this is my last slide on the AHCAL. The SEPM will also be improved. You see here a new generation of SEPM, and they are compared to the old one in terms of direct rate versus trigger in photoelectron. So this is expected to improve the signal over background for the AHCAL. For the SD HCAL, it is also needed to produce a technological prototype, but the problematic is different. Because, well, the electronics was already embedded, the challenge is more related to the mechanics, because the largest chambers will be 3 meters times 1 meter. But this technological prototype will be used also to improve the electronics and to include the timing as an option. And the aim is really to have an ILD module 0 that is now under construction. So one of the improvements related to this large size of the chambers is the way the gas is circulated in the RPC chambers. This is the old way to do it, leading to some inhomogeneities. This is how it will be done with the new chambers. And also the production of large-scale planes for these 3 meters RPCs fulfilling the planarity requirement was demonstrated. And okay, last slide for conclusion. The readout will be also improved. New ASICs, ASRoC3 will be included. The clock will be transmitted not with HDMI but with TTC fibers, exactly as for LHC experiments. And the new chip, the new ASRoC3, will have an extended dynamic from 15 to 50 picoseconds. So the conclusion, CALICE proposes some technologies for the hadronic calorimeters that are optimized for particle flow approaches. Here I focused on two, the analog hadronic calorimeter and the semi-digital hadronic calorimeter. Two physics prototypes were produced and validated in test beam. They show very good performances. However, now new prototypes are being produced in order to show that they can be scaled at the size of full experiment like ILD. They are expected to be ready this year. Now, one remark concerning the SD-HCAL was initially developed for ILD, but there are some improvements that are envisaged and even implemented, like the timing, and also to add an active cooling that is necessary in the case of circular colliders where you cannot use the power pulsing. And there are still many ideas and tests and developments being done.
Thanks so much. Question, comments?
Yeah, I have a few questions. The first one is about the software compensation, and so you mentioned that software compensation for the AHCAL. So I wonder if it's possible to do the software compensation for DHCAL as well.
It's more or less done.
It's almost done. By using the threshold information, we are using this to compensate for the saturation, etc. So it's
okay. So how
somehow it's used.
How do the two types of calorimeter compare in terms of the software compensation performance?
Yeah, I mean, maybe I can say a few words. For the time being, we don't have results from the technological prototype of AHCAL. They are taking data nowadays. If you compare with the previous, which is the physics prototype, the electronics was not embedded on the detector, it's what outside. Okay. So if you compare, I mean, with the resolution, if you look at if you could put at high energy, you can see that we are reaching most between 7 to 8%, or I mean, the relative resolution. Mm-hmm. In their case, they are reaching 6%. But it was with the physics prototype, so we're waiting to see the results with the technological prototype. I expect that we'll have similar results.
Okay. Yeah, maybe my second one is about the track segment reconstruction that you talked about. So again, you know, because you showed in the track segment reconstruction results for both the DHCAL and the AHCAL. So again, my question is, I want to know how these two compare in terms of the track segmentation, segmentation reconstruction.
Well,
yes.
This is strongly related to the segmentation. Obviously, it's more easy to reconstruct tracks if you have fine hits. And you see it from here, if you compare the multiplicity of the tracks, because these are comparable showers, and these are the tracks reconstructed in the SD-HCAL, and these are the tracks reconstructed in the AHCAL. And you always have, it's natural, less tracks in the AHCAL as SD-HCAL. And this is really due to the segmentation.
Okay, so yeah, these are from simulation.
No, these are data. The points are data.
Yes, yes, the right black points are data. Okay, but yeah, these are like for from the single hadron events. So what if we have like a jet where we have a lot of particles in a small region? So in that kind of environment, can we still do a very good job in the on the track reconstruction?
If you have overlapping showers below some distance, yes, but otherwise.
I mean, just to say, maybe if you allow me, in this treatment, at least for the SD HCAL, the treatment consists in eliminating the very dense zone, okay? Because otherwise you cannot build with the half transform. So we start by cleaning, and then we apply the recipe. So either in jet or in hadronic shower, it's very dense. So you have really to clean before to start. Okay? And in addition to this, you have, I mean, this maybe here it was for the prototype without magnetic field, but we developed also to apply half transform within the magnetic field because you have a spiral tracks. Okay, so it's more sophisticated than that, and we are able to find these tracks.
Okay.
Any other question, comment? If not, we move to the next speaker.